is that last week we had gotten, we derived the small strain tensor. We saw how this small strain tensor is actually the symmetric part of our displacement gradient, right? So I've written out the expression like so, but this is actually equal to del naught u ka symmetric part. So इसके ऊपर ना एक what we need to discuss is basically कि क्या हो रहा है when we are taking the gradient and we're looking at the strains from it. So essentially, if you notice, then I have an infinite, मतलब on the left hand side of the equation, I have something with 6 terms. ठीक है जी? By the way, I say 6 because it's symmetric, right? So I think I should actually point that out. So actually, small strain tensor is a second order tensor. It's a dyad, which means that it has a total of 9 terms, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 as it is. But the thing is that it is symmetric. मैंने अभी बोला ये था कि it is the symmetric part of the displacement gradient. So which means कि it's only these terms which are unique. So the diagonal ones and then just the off diagonal ka ek representation, and the rest it is symmetric. So I'm just going to represent it like so, represent it like so. So I have only 6 unique terms for my infinitesimal strain tensor. And how they're coming about is that I'm taking the gradient of displacement, which displacement is actually just 3 terms, right? U would have been just U2, U3. So इस इशू की वजह से ना कि हम कुछ 3 terms से सिर्फ 3 sort of variables को differentiate करके I'm getting 6 unique terms. There is a little bit of issue of compatibility that we need to consider कि हम equation की कौन सी side से कौन सी side पे जा रहे हैं. Now let me explain what I mean by that. So for example, consider करें कि मेरे पास सिर्फ कोई 3 displacements हो, ये U1, U2, U3. तो अब तो मेरे पास क्योंकि ये 3 unique U1, U2, U3 है, so if I want to find my strain tensor, मैं straight forward उसका gradient निकाल के उसका symmetric part निकाल सकती हूँ. ठीक है जी? मतलब इन 3 को लेकर I can find each of these क्योंकि वो 3 फर्क तरीके से manipulate हो रहे होंगे. But if I have my strain tensor, मतलब ये कि I start from my left hand side of the equation, then I get into a little bit of a trouble because I think you might notice what the issue is. Okay, I'm starting with 6 terms and I have to get to 3 terms, which means कि there has to be, मतलब मेरे पास ज़्यादा equations हैं और कम unknowns हैं. Right? So my point here being that there has to be some sort of a relation itself within these 6 terms. So that is, they're not completely independent. Basically, they're unique, but they're not independent. Such that उन 6 से मेरे पास जिस तरह मर्जी मैं उन 6 को यूज कर लूं, मेरे पास वही 3 displacement की terms आए. Okay? So the point being, if I go from U to epsilon, no issue, all good. 3 से 6 पे जा रहे हैं. But when I go from epsilon, I go from 6 terms to 3 terms, then there is a little bit of a question mark, which is कि I have to make sure कि वो 6 की 6 मुझे जिस तरह मर्जी मैं उनको ले लूं, I do get the same displacement back from them. So does that make a little bit of sense? ये थोड़ा सा, it's always a little bit more difficult to explain mathematically कि क्या reason है. Could someone please confirm कि ये कुछ समझ आ रहा है या नहीं?
as such clear नहीं हुआ ये point.
Okay, so let me explain again. So basically देखिए मेरे पास जो displacement है उसके 3 components हैं, है ना? U1, U2, U3. अब जो epsilon है, that's just a function of these 3 का gradients ले लेके, है ना? तो अगर मुझे ये वाला epsilon 1, 1 निकालना हो, then I just मैं उसी U1 का x1 बस दैट्स इट एक्चुअली u1 का विद रिस्पेक्ट टू x1 है, तो वो मैं निकाल सकती हूँ। फिर मुझे एप्सिलॉन 1 2 निकालना हो तो अगेन उन्हीं तीन को लेके आई नो कि मुझे उन्हें कैसे मैनिपुलेट करना है सो दैट आई विल गेट माय एप्सिलॉन, राइट। वेयरएज अगर मतलब ये कि इन तीन का ग्रेडियंट फर्क तरीके से निकल सकता है सच दैट आई गेट द 6 terms of the strain gradient. Whereas if I start the other way around, which is कि मेरे पास एप्सिलॉन की 6 टर्म्स हो, so that means एक किस्म का कि मेरे पास कुछ 6 इक्वेशंस हैं और एक्चुअली उन 6 इक्वेशंस से मुझे वापस आई हैव टू गो बैकवर्ड्स सो टू स्पीक, आई वांट टू फाइंड के व्हाट वर द displacements which had caused this strain. So I'm going from 6 equations to 3 unknowns in a way. Now this is like an over क्या कहते हैं overposed problem, मतलब मेरे पास ज्यादा unknowns हैं कम sorry ज्यादा variables हैं कम unknown है, तो इसके अंदर this is what I'm trying to say कि there has to be a way to ensure कि अगर बेशक मैं epsilon 1 2 लेके u1 और u2 निकाल लूं या फिर मैं epsilon 2 2 से सीधा u2 निकालूं, तो जो मुझे इससे u2 मिल रहा है, देखें एप्सिलॉन 1 2 जो है दैट विल बी अ कंपोनेंट ऑफ u1 एंड u2, तो वो जो एप्सिलॉन 1 2 है उससे मुझे एक कोई वैल्यू ये u1 और u2 की मिल रही होगी, और फिर जो ये एप्सिलॉन 2 2 है उससे मुझे एक और भी मिल सकती है। सो दे शुड गिव मी द सेम वैल्यू, इनमें आपस में कोई डिस्क्रिपेंसी नहीं होनी चाहिए। That's what I'm trying to get at. So when I have more equations than unknowns, then what I actually need is that there has to be some limitations imposed on this strain tensor to ensure कि जो मेरे पास displacement field निकले इनकी फर्क फर्क terms से वो सब आपस में compatible, मतलब उनमें आपस में कोई discrepancy ना हो। और इस चीज को ना कहते हैं that we have to ensure that the strain is compatible. Okay. For anyone जिसके लिए अभी भी clear ना हो, अभी देखिएगा मैं आपको example करके दिखाती हूँ and then I think उससे it will become even more clear what I'm saying कि we have more strain components and we have fewer displacements, so there has to be some sort of a check on those strains ताकि हमारे पास सारी की सारी displacements आपस में compatible निकले। Okay, let's see the example. Okay, मैंने ना एक arbitrary strain field choose की है और उसका I will see whether this is something which is physically possible or not. यही बात इसके ऊपर हम अभी end तक ना I think ये clear हो जाएगा. So let's see what my strain field is. That I just have an E11 epsilon 11 component. Please allow me कि मैं कभी-कभी epsilon को E कह दिया करूं. And all the other strain terms are 0. That means that what I have is that epsilon as a tensor is just kx2 whole square 0 0 0 0 0 0 0 0. Now the thing is अगर if you just look at it like this और आपको कुछ ना पता हो कि okay ये strain किसी एक displacement field से आना था, मतलब ये कि ये एक u1 u2 u3 था, कोई displacement थी which caused this strain, or you had not thought about this कि okay I have 6 components, वही बात ना unique है। Oh, sorry. This triangular part is what I needed. Okay, these 6 components are actually coming from these 3, and if you had not thought about it, तो फिर आप कहते हैं कि हाँ मैंने हाँ कोई random strain field, sure why not, कोई भी random strain field उठा के मैं ले सकता हूँ और वो physically possible है। Whereas अभी हम जरा इसको check करते हैं कि अच्छा ये मेरे पास 6 terms तो हैं, लेकिन इन तीनों ने आना इन 6 ने इन 3 terms से calculate होना था। तो इज इट एक्चुअली पॉसिबल कि मेरे पास ये 3 टर्म्स हो और इनसे ये 6 मिल रहे हो या नहीं? To do that, what I'm going to do is I'm going to work backwards. I'm going to try to use the epsilons to find the displacements. If I do that, let's start first with the first term. Now, I know कि मैंने जल्दी से उसकी equation गुजार दी थी, लेकिन I hope आप सबको small strain tensor का थोड़ा थोड़ा तो याद ही होगा. Eij is actually equal to what? It's half of ui comma j plus uj comma I, where remember that these commas represent partial derivative, okay, with respect to the material description of position, that is capital X's ke hisab se this displacement gradient is being defined. Okay, so if I am looking at epsilon 1 1, matlab jab I और j दोनों 1 है, so then this becomes u11 plus u11, so half 2 से cancel हो जाएगा, so I just get epsilon 1 1 is equals to u11. ठीक है ये बात. So what this means is I get that my u11 is strain field में given थी, it's kx2 whole squared. So I just pop in that my u11 is equals to this strain की value kx2 whole squared, right? अब now please notice, I know I've skipped a few steps. I was just hoping कि थोड़ा skip करने से you will get the hang of how quick we need to be with our sort of analytical ability. ये u11 होता क्या है? This is del u1 with respect to del x1, and now this is equals to kx2 whole square. So if I want to just find my u1, clearly I need to integrate this equation with respect to capital X1. And if I do that, वो integration क्या बन जाएगी? So I have to integrate this with respect to the x1 या फिर. So integrating this, what do I get? इधर तो कोई है ही नहीं term of x, तो x1 सिर्फ in the linear or term आ जाएगी. So this would become kx1 x2 whole squared, right? Plus of course partial derivative था ना. So this is actually partial. क्या मुझे थोड़ा सा मेरी calculus के लिखना भूल गया. It's integration with respect to a one variable only. So इस term में तो x1 directly वैसे ही आ गया, but this could also have any constant terms of the other variables, x2 and x3. Why? Because जब ये मैं f function, any function of x2 और x3 को include करूं, तो इस function के अंदर कोई x1 की term नहीं होती, such that when I take the partial derivative of this expression with respect to x1, then this term just goes to 0. है कि नहीं? And I get back what I know कि था मेरा u, the partial derivative of u1 with respect to 1 must just be kx2 whole squared. ठीक? So my puri integration, my complete integration must include this function, arbitrary function. I don't know what it is. I don't know what this f is, but it is a function of x2 and x3. Okay? Yeah, is this part clear to everybody? Yeah. कोई किसी को अगर unclear है तो please just say the word. Okay, great. तो सबको clear है. तो इससे I basically I found what my u1 is. Now let's see. Okay, मेरा epsilon 220 है. मैं अगले पे move कर रहा हूँ. I'm gonna jump to finding these three, right? That's what I'm trying to do. So मेरा मैंने epsilon 11 use करके u1 find कर लिया. अब I'm gonna use epsilon 22 to find u2. इसी तरह epsilon 22 को जब मैं integrate करूँगी, then I'll find my u2. और this time around, because epsilon 22 is just 0, then the integral of the 0 is just some function with which is some function of x1 and x3. मतलब ये कि अब इसके अंदर कोई x2 नहीं हो सकता, such that when I differentiate this partially with respect to 2, I would get a 0. Right? Clear to everybody? This g is just a function of x1 and x3. I'm not getting any response. I'm just hoping it's clear. Right? Excellent. तो अब हमारे पास एक u1 और u2 आ गया है. तो लेट मी सी कि अगर मेरे पास ये U1 और U2 गिवन हो, जो मैंने अभी फाइंड किए अपनी अपेरेंटली इस स्ट्रेन फील्ड से, तो मेरे पास एप्सिलॉन 1 2 क्या आता है, राइट? एप्सिलॉन 1 2 जरा निकालते हैं. लेट्स फाइंड एप्सिलॉन 1 2. व्हाट वुड दैट बी? आई डोंट नो मैंने लिखा है या नहीं, इसलिए मैं ओके आई शुड प्रॉब्ली. एप्सिलॉन 1 2 वुड बी व्हाट? हाफ ऑफ ये ऊपर एक्सप्रेशन देखिएगा. It would be del U1 with respect to del X2 plus what? Del U2 with respect to what? Del X1. Right? All this everybody agrees this is what epsilon 1 2 is, right? अब जब मैंने U1 और U2 निकाल लिए हैं, तो मैं जरा सब्स्टिट्यूट करके देखती हूँ कि मेरे पास epsilon 1 2 क्या आता है. और when I do that, I know sorry घिचपिच हो गया थोड़ा, लेकिन जरा गौर से देखिएगा. Now U1 with respect to U2, सबसे पहले ये del U1 with respect to del X2, ये मैंने एक्सप्रेशन निकाली थी ना, इसको जरा पार्शियली डिफरेंशिएट करें with respect to X2. what do we get? ये 2 will come down, so I get 2k x1 x2. एक तो ये टर्म आ गई 2k x1 x2. Then I have this function of x2 and x3. Now this is a function of x2 and x3, which means कि इसका partial derivative with respect to x2 exist करता है. So that's why I've just written that one down as it is. I don't know what it is, so I have to just write it as del f of del x2. So this is u1 with respect to x2 done. Now let's see u2 differentiated partially with respect to x1. u2 क्या था? It was this one. G of x1 and x3. So differentiating this expression with respect to x1 just gives me the partial derivative of g with respect to x1. Why? Because इसके अंदर एक x1 है. Right? Now what is the issue with this? The issue is, अब जरा प्लीज गौर से मुझे थोड़ा सा और आपका अटेंशन चाहिए. The issue is कि इस टर्म के अंदर तो x1 है, whereas this was a function of x2 and x3. अगर मैं इसको डिफरेंशिएट कर भी लूं x2 के टर्म्स में, this will not be this will never be in terms of x1, this one, right? Similarly, this thing, this term right here has x2 inside it. तो ये जो ये तीसरी मेरे पास टर्म आ रही है, a function of x1 and x3 being differentiated with respect to x1, neither will this ever be in terms of x1 and x2. So when both of these are not in terms of x1 and x2, तो इसको तो ये cancel कर ही नहीं सकते. So whatever I do, this will never equal to 0. And this is a problem for me because to begin with, मैंने तो कहा था कि जी मेरा ये strain tensor है kx2 whole square 0 0 0 0 0. So I had claimed that this was my strain field. And now I'm finding out कि अगर मेरे पास epsilon 1 ये हो और मेरे पास epsilon 2 ये हो, epsilon 2 2, then epsilon 1 2 जो मैंने 0 लिखा हुआ है, that is just not possible. Right? That is, this strain field which I had just written down randomly is actually not compatible. उसकी terms आपस में compatible नहीं है. They do not lead to the unique U1, U2, U3 that we need, basically. Or that's what I was trying to say, कि हमारे पास we have 6 sort of strain terms which are arising from 3 displacements. So there actually has to be some limitations on these 6 ताकि हमारे पास इन 6 की 6 से whatever I do, अगर मैं epsilon 1 1 निकाल के U1 निकाल लूं या epsilon 1 2 को यूज करते हुए U1 निकालूं, I should get the same displacement. ऐसा नहीं होना चाहिए कि इसकी एक टर्म से एक डिस्प्लेसमेंट आ रही हो, एक से कुछ और आ रही हो, एंड सो ऑन. So this is the condition of compatibility which we require on strain fields, essentially, right? और ये थोड़ा इसकी mathematical sort of explanation है, लेकिन I'll just explain also what that means physically. लेकिन उससे पहले I just do need to say कि वो limitation फिर हम क्या impose करते हैं. और again, how we find that particular limitation is done using arithmetic and maths, but it's a little bit more advanced calculus, so we're not going to consider that in our course right here. So for us, it's sufficient to just know कि हमारी strain field के लिए ना compulsory है that it has to satisfy this equation so that we can make sure that it is compatible. So that we can make sure कि जो हमारी पिछली स्लाइड में जो हमारे साथ इशू हो रहा था ना वो ना हो. And this is known as the condition of compatibility, so to speak. Okay. Somebody has their mic unmuted. Any question?
Yes, ma'am. Last slide में जो U1 है
जी.
उसके अंदर बिफोर दैट जैसे हम लोग एप्सिलॉन ई यानी E11 जो था वो kx2 स्क्वायर था.
जी.
How did it get kx1 and x2 स्क्वायर?
देखें,
ये थोड़ा समझ नहीं आया.
मैं बताती हूँ आपको. ये देखें, हम ये जो था ये U11 with respect to del x1, right? This E11 जो होता है यही है ना? You agree with this?
Yes, ma'am.
So this is equal to now what? Kx2 squared. Now please notice कि ये differentiation है with respect to x1. तो when I integrate this, अच्छा नहीं सॉरी, इंटीग्रेट करने से पहले जरा क्लियर करते हैं. अगर हम पार्शियल डेरिवेशन विद रिस्पेक्ट टू x1 देख रहे हैं तो जब विद रिस्पेक्ट टू x1 है तो बाकी वेरिएबल्स तो एज अ कांस्टेंट कंसीडर किए जाते हैं ना, राइट? सो दिस इज जस्ट एज इफ के मेरे पास कोई के खाली के हो, मतलब समझे एक कांस्टेंट है बस मेरे लिए, क्योंकि मैंने x1 के लिहाज से मैं देख रही हूँ. दैट्स माय variable that I'm differentiating with respect to. So it's as if this was just some constant k. अब इसको देखें, अगर एक मैं constant को integrate कर रही हूँ with respect to x1, then wouldn't it just be, अब now I'm performing this integration, wouldn't this just then be u1 is equals to kx1?
Right, ma'am. सही है.
Right? अब please remember this k was actually equal to kx2 whole square. ये small k है. Hence why this is kx1 x2, right?
Right,
Ma'am, I have a question.
Yeah.
Ma'am, we considered an arbitrary strain field here, and as we know कि हमने कुछ calculate नहीं किया तो most probably these terms would not correlate to each other like E11, E12 or E22. So अगर हम drive करते हैं इसको proper by using components of U1, U2, U3, is it still any possibility that our EIJ would not be compatible?
Not at all. So this is what we had started off with discussing. Okay, if we go from the displacement to the strain, then it is guaranteed that the strain field will be compatible. Why? Because हम already 3 correct unique displacement से आके उनको use करके strain को find कर रहे हैं. ठीक है? So that's why I put के अगर if you're going from displacement to the strains, no issue. हमने सिर्फ उनके derivatives निकालने हैं और strain find कर लेने हैं. कोई मसला नहीं है. It's only that we have to check for compatibility for the strain. अगर हम strain खाली हमारे पास given हो या known हो for whatever reason, then that strain must fulfill compatibility. Okay?
Okay, ma'am.
It's going from strain to displacement, which is the issue sometimes. So yes. लेकिन अदान आपने कहा कि ये हमारे लिए ऑब्वियस था कि मैंने कोई रैंडमली स्ट्रेन, आई डोंट थिंक दिस वाज ऑब्वियस टू एवरीबडी कि देयर हैज टू बी सम सॉर्ट ऑफ लिमिटेशन. द स्ट्रेन कैन नॉट बी जस्ट सम सॉर्ट ऑफ अ रैंडम components. There actually has to be some limitation on the strain variable basically, or the strain tensor, and that, as I've just discussed, is known as the condition of compatibility, which is required for strain. Or as I said, I'm not going into the derivation of it. It's just you take my word for it. For the small strain tensor, please note it, epsilon likha hua hai. Epsilon is the small strain tensor. The condition of compatibility is this one right here. It's a double cross product. So it's the del crossed with epsilon crossed with del again, and this must be equal to 0. अभी मैं इसको बड़ी अच्छी तरह डायरेक्ट नोटेशन में लिखा हुआ है. This gets pretty complicated when we actually start to figure out कि ये what each of the terms are in this. So this is I can't, मुझे अभी भूल गया actually. I'll have to think about and या फिर directly कहीं से देख लें, या फिर I'll have to calculate कि ये this would be how many terms or how many components would there be in this. I think this would be I j 1 2 3 4 maybe 1 2 3 4. So this would lead us to a fourth order tensor, which means it would have some 81 components. But then because strain is symmetric, तो 81 से थोड़ी कम हो जाएंगी, लेकिन still it's a large number of equations contained within just this tensor equation right here. Just also a side note, okay, this is the compatibility equation या condition for the small strain tensor. For the green strain tensor या फिर for the large strain tensor, the compatibility condition is actually written out a little simpler. When we have large deformations, then the compatibility condition is actually in terms of the deformation gradient itself. And that is just that the del crossed with f must be equal to 0 for the case of large deformations. Okay. Now, of course, this is the more general result, right? Large deformation के results जो हैं वो small deformations पे भी apply होते हैं, whereas the small deformations are the more specific result than this one. Okay, the reason why we've got both here is because, of course, आप लोगों ने देखा अपनी engineering में, how many times are you referring to the डिफॉर्मेशन ग्रेडियंट? कितनी दफा आप लोगों ने जिंदगी में पहले निकाला था? Most of the time we are talking about the small strain tensor, which is why हमें compatibility condition हमारी small strain tensor की term में चाहिए होती है, rather than just the deformation gradient. Okay, so that was a side note. Now let me just expand this out in the index notation. Okay. Whew. Yep, I do not expect you guys to know. I did not solve this myself. I looked this up in a textbook. So if you actually perform this double cross product on the strain tensor in this order, you get this result. So मैंने आपको कहा था कि 81 की terms, लेकिन इसमें actually ये dummy है. So it does lead back to a second order. So which means it leads us back to how many? It leads us back to 9 equations basically again. So because of the symmetry of the strain tensor, right? So, oh, okay, actually not even 9. So 6 are unique. Again, sorry, this maths I'm not going to keep up with. Pata nahi how long it would take us to figure this out. So we're just going to not trust, but look these things up in a textbook, because these are pretty involved calculations, right? So there are 6 unique equations for the condition of compatibility for the strain tensor. Again, ये 6 भी हमारे लिए थोड़ी ज़्यादा हैं for 3D. So what I'm going to do is I'm just going to consider the case when we go in 2D. And luckily for us, the nice thing is that when we are talking about 2D problems, so by the way, 2D के लिए I think I'd have to actually explain what I mean कि 2D में कहाँ से आ गए हम. 2D का मतलब ये है कि जब हम plane strain problems को देख रहे हों. Plane strain का मतलब ये होता है कि we are looking at a problem in which a specimen, actually I should probably ask you guys this, let's test your undergraduate knowledge. Who here knows what plane strain is? What is the strain tensor for plane strain? Could anyone comment in the chat? What is plane strain?
A 2 by 2 matrix, man.
It's a 2 by 2 matrix, yes. Why is it a 2 by 2 matrix, plane strain mein? Why?
Because we
बाकी
are
terms
considering only 2 directions only here, not the third one. So
नहीं
it
तो
will
हम
be a
अगर ना
Rank 1
कंसिडर
tensor.
करें हम ना कंसिडर करें, does that mean कि वो गायब हो जाएगी? मतलब why can we ignore that direction is the question.
It's a rank 1 tensor.
It's a sorry.
ma'am,
It's a rank 1 tensor.
Um, actually, so it's still strain and it's still a second order tensor. It's still a dyad. It still actually has 9 terms with 6 unique terms and so on and so on. It's just, so basically it just so happens that some of the terms are 0. That's what plane strain is. So plane strain is a case when we have something which is so thick. Let's say I'm standing across a wall. It's so thick in the direction of the wall. I can consider that all itna iska ye, let's say कि नहीं मैंने बहुत ही, so consider कि thickness uski into the wall and something like this going into the page. It's so thick in that direction that all my अगर ये z direction है into the wall, that it's always with respect, the strain is with respect to the original dimension, right? So if the original dimension is so thick that there are actually, it could be considered to be infinite in a way compared to the small delta z's that might be happening in it, such that the z strains all then go to 0 because it's just so massive in that direction. So that's why I was saying imagine आप लोग एक दीवार के across खड़े हुए हो, मतलब या फिर एक दरवाजा खुला हो और आप उस दरवाजे के अंदर खड़े हो के दीवार को अंदर की तरफ देख रहे हो, then it's pretty large in that direction. This holds true for many problems, assuming कि हम उसको किस तरीके से देख रहे हो. So even for, let's say अगर मैं किसी electronic chip को देख रही हूँ, I can actually still consider that अगर मैं उसको कुछ particular sort of assumptions or simplifications ले लूँ तो. So the plane strain condition actually does arise very frequently. And what I was saying was that because of its large dimension in one direction, we can assume all of the strains in that direction to be 0. So I was trying to draw the z direction to be very large into the slide. Okay, into the slide it's so large कि मेरे सारे जो z direction वाले strains हैं, they're all just 0. And of course this is symmetric as well. So what I just end up getting is that I have an epsilon 11, an epsilon 12, and an epsilon 22. That's it. And that's why we can represent it either as a second order. यहाँ पे, remember there are terms here. I can either represent it as a second 2 by 2 matrix, या फिर as somebody else was, you were trying to say, I get what you were saying. You were just saying कि उसकी 3 terms होती हैं. So और उसको often फिर column vector में represent कर देते हैं. You're completely right about all of that. But actually what's happening is that our strains in the third direction are 0. So we just assume which will just be 1, 2 as well. We just assume that we can look at just the 2 by 2 one. Or in this case, this plane strain, ye plane strain hai, okay? So please everybody remember this. So for this particular case, it turns out that the compatibility condition, jiski 6 pehle 3D ke andar actually 6 equations hai, they simplify even further and actually collapse onto just being one unique equation. Or that one unique equation in terms of these terms, epsilon 11, epsilon 12, and epsilon 22, is just this one right here. Okay, and index notation is this one. or what I'll do is I'll write this down in sort of differential की comma को हटा के del operator डाल के ताकि it becomes even more clear. So this is just the one equation that we need to satisfy in order to ensure कि हमारी strain field compatible है in 2D in the case of plane strain. ठीक है? Yes. So बजाय ये कि last slide the example that I'd considered, this was a plane strain problem even though I hadn't said it, but please notice कि उसके third direction के strain zero थे. So instead of finding this U1, U2 and so on, I want you guys to try out कि आप लोग घर पे ना इस पे compatibility equation लगा के try कीजिएगा. And you will basically see, because we've already shown that was not a compatible strain field, you will see that this will not turn out to be zero. And that's the issue, right? That it was not fulfilling compatibility. Okay. So you do not need to memorize this equation. Of course. Actually, you basically do not need to memorize any equations for this course. These things will be provided to you. So this equation of compatibility for plane strain will be provided to you. This equation for क्या कहें जो 3D general है ये भी अगर if you need it, it will be provided to you. You don't need to memorize any of this. You just need to understand what these things mean. Right. Okay. So we've done the maths of this. Let's just see actually the important part. Okay, what does this mean? ठीक है जी. और मैंने आप लोगों को वो मैथ्स का समझाने की कोशिश की थी कि वो 6 स्ट्रेन से 3 यूनिक आने के लिए हमें कंपैटिबिलिटी चाहिए, लेकिन एक्चुअली सादी जबान में इट्स एक्चुअली मच मोर easy to understand. The point is basically it goes back to our basic assumption of the continuum. And if you recall in our first lecture, we discussed how we assume that in a continuum, there can be no gaps or overlaps in the continuum body. मतलब matter के अंदर कोई gap या overlap नहीं हो सकता. Now what this means is basically कि consider कि हमारे पास directly आ गया, लेकिन just consider कि मेरे पास original एक body ये हो जो in 3 lines से it's just made up of these 3 lines. And what compatibility is trying to say is कि it's not possible कि I have a displacement या a strain field जो इस तरह की deformed body बनाए. Because what's happening here is कि number one, there's an overlap right here. So there's an overlap. Secondly, ये कहाँ से ये क्या overhanging? What this makes no sense in a continuum assumption, right? What is this? Is this matter? Is this not matter? मतलब it's like a weird little overhanging gap sort of in the it doesn't make physical sense with the continuum assumption. So that's why this is not a compatible deformation. Whereas this thing, so is tarah ka it was like a slightly bigger triangle, and then it goes back to sort of even after deformation, hamari body is still something which has no gaps and no overlaps in it, then that is compatible. So that's what compatibility means physically, basically. और ये जो mathematical expression हमने लिखी हुई है ये वाली, that's just ensuring that that's the case for the field that we've written down or we have or we've calculated or whatever it may be. Okay, so I hope it makes sense now. Compatibility. Yes, so it just, yep, this is a good way to put it. It makes sure that all of the particles of our body, they fit back together without any overlap or any gaps between them. Okay, all of those particles, the elements to मैंने use किए थे because I was using the lines as an example, but it's about the particles in the body, right? So that's what compatibility means, right? Any questions? Hassan, sorry मैंने आपका पहले मिस कर दिया था, ये बताइएगा, what are you asking when we consider shear and axial strain? What do you mean? Hassan या Hassan? चलें, Hassan और Hassan is not speaking, so इसलिए I will carry on. Mic issue, okay. So चलें, you keep typing and then we'll see what what the question was. We'll come back to it, no problem. Right, okay, so moving along, just picking up a little bit of pace, okay, there are also other interesting properties of the strain tensor that we might be interested in. Remember strain tensor, okay, A epsilon ij, it's epsilon 1 1, epsilon 1 2, epsilon 1 3, epsilon 2 2, epsilon 2 3, and epsilon 3 3. These are just the unique terms. Baki, it's symmetric, so that's why I haven't written down. Now, I think you guys may recall that there are something known as the eigenvalues or eigenvectors of a matrix, of a square matrix. So if you notice that we can write down a second order tensor as a square matrix, it's a 3 by 3 square matrix की terms में उसको represent कर सकते हैं. तो इनके भी हम in strain tensor का भी हम eigenvalues निकाल सकते हैं. लेकिन mechanics के अंदर ना more commonly these eigenvalues are referred to as principal values. They're the same things. They're exactly the same thing. But they're just more commonly known as the principal values. और अगर किसी को अब थोड़ा सा भूल गया हो तो just a little reminder कि matrix notation के अंदर eigen value और eigen direction जो थी, eigen vector, how they're represented is basically that if we can find a vector which if we multiply it by the matrix, so A हमारा matrix था, उसको multiply किया by the eigen vector, then that can actually be represented as just a scalar multiplied by that same eigenvector. Okay, so then this lambda is my eigenvalue and this n would be my eigenvector. तो इसको calculate करने के लिए भी हमें इसी चीज को manipulate करना होता है. This definition of the eigenvalue and eigenvector को, which we'll just do shortly, but then again not recall, I'm telling you that this is it's pretty maths. It's actually not maths heavy, but it's notation heavy, this course, but this is not a maths course, right? So I don't expect you guys to remember how to calculate the eigenvalues. Instead, we'll just see कि expression क्या होती है और हम वो final result जो है ना हम उसी को directly use कर लिया करेंगे whenever we are working in continuum mechanics. So the point is, whenever we have if we have a 3 by 3 matrix, फिर उसकी 3 eigenvalues होंगी, which I'm representing as lambda 1, lambda 2, lambda 3, and 3 eigenvectors, which are n1, n2, and n3. Okay, and how they're found, as I said, is by solving this equation. इसी को manipulate करके, that is, we take the right hand side to the left hand side, and then we solve this particular thing. And this equation actually turns out to be only true if the determinant of this inner, जो पहला product है ना, that is equal to 0. ठीक है जी. Again, as I said, I know maybe आप लोगों को भूल गया हो, लेकिन we don't need to be concerned by that. So that's how we find eigenvalues. और because we have a 3 by 3 matrix, इसका determinant जब हम निकाल रहे होंगे इस चीज का, इस term का, that will give us, when we're trying to find its determinant, it will give us a cubic polynomial. That is, it will go up to the power of 3, and when we solve it, we'll get our 3 eigenvalues. Interestingly, इस चीज को हम generally solve कर सकते हैं, मतलब ये कि हम इसका general result लिख सकते हैं, which is कि वो determinant equal to 0 होने का मतलब basically ये है, this one equation. It's very useful, extremely powerful and extremely useful, that the eigenvalues of a 3 by 3 matrix, या फिर a second order tensor, must satisfy this equation. So lambda cube minus I1 lambda squared plus I2 lambda minus I3 equal to 0, etc., etc. Now, what is I1, I2, and I3? It turns out that these are actually also some special properties of the tensor, या फिर of the 3 by 3 matrix. And they have a special name. they are known as the scalar invariants of that matrix, जो वो 3x3 matrix हमने शुरू की थी ना जिससे, उसके स्केलर इन्वेरिएंट्स को ये I1, I2, I3 कहते हैं। और रिस्पेक्टिवली ये मैंने रैंडमली ये I1 और I2 नहीं लिखा हुआ, ये they are actually, this I1 is the first invariant, I2 is the second scalar invariant, and I3 is the third scalar invariant. और इनको in 99% of maths and continuum mechanics and mechanical engineering literature, you will find them to be represented by I. Okay. इसलिए this I is also special. And what these are, they're as I said, ये कुछ special चीजें हैं उसी matrix की. So I1 जो है ना, वो ये होता है. It's just AII. I'm gonna ask you guys actually. So I1 is this AII. What is that of the 3x3 matrix? Post it in the chat, please. किसी को याद है ये I से?
Trace.
Exactly right. Okay, thank you. Pop it in the chat, please. रबिया ये मुझे नहीं पता ये diagonal terms क्या होती हैं. But yes, it is the trace. I1 is the trace of the 3x3 matrix. Okay, and then I2 is this special thing. Again, it's just easy to represent it as an index notation like so. ये actually क्या होता है? This is the determinant of the co-matrices जो उसके अंदर होती हैं, कुछ ऐसी सी चीज होती है. I'm forgetting, sorry, इसलिए please ignore. I'll look up के second invariant exactly क्या होता है. लेकिन in index notation, it's nice and easily represented by just one line, so that's useful for me. And then finally, I3 जो है, that's actually the determinant of the original 3x3 matrix. So the point is, okay, these three things, for whatever 3x3 matrix we may have, we can find them. And once we can find them, फिर हम ये equation solve करके उसके eigen values को निकाल सकते हैं. तो यही procedure, of course, हम एक strain tensor के लिए भी कर सकते हैं. ठीक है? Now that's what I wanted to get into. अभी तक तो ये मैंने बिल्कुल general बात की है of a 3x3 matrix. So you can apply this to any second order tensor. So let's just discuss that when we do this procedure for a strain tensor, then what do we get? We basically find the principal values of the strain tensor. और of course, क्योंकि वो strain tensor की principal values हैं, that's why they are known as principal strains. अब ये principal strains को ना हम आम तौर पे represent करते हैं as epsilon 1, epsilon 2 and epsilon 3. Please remember 3 eigen values आनी थी ना. So इसलिए this why this an epsilon 1, 2, 3. लेकिन बड़े ध्यान से इसके साथ रहिएगा, because please notice ये सिर्फ एक index है. This is not कोई double index की बात नहीं हो रही. मतलब ये कि ये index notation वाले strains नहीं हैं, ये बस उसकी eigen values हैं. इसलिए epsilon 1 है और epsilon 2 है और epsilon 3 है. Got it? तो वो जो 3 lambda 1, lambda 2, lambda 3 आना था ना हमारे पास for epsilon ij, उनको हम as epsilon 1, epsilon 2 और epsilon 3 लिख देते होते हैं. और yes, so these are the principal strains and they are actually pretty important physically, because physically they represent our एक material point पे के maximum normal strains उस point पे क्या हो रहे थे, या उस particle के maximum normal strains क्या थे. Okay, sorry, maximum and minimum, मतलब maxima या वो थे normal strain. If you guys recall now from your undergraduate education, you may have encountered something known as Moore's circle of strain. किसी को याद है ये बात? Moore's circle for strain. और उसके अंदर what we used to do was we used to plot our strain state. अभी मैं 2D का करती हूँ. We used to plot our strain state on this graphical representation जिसमें x axis पे होता था normal strain और y axis पे होता था वही हमारा engineering shear strain gamma। और फिर भी हम एक कोई भी मटेरियल जो हमारे पास एक सॉर्ट ऑफ ये मटेरियल का पॉइंट था और हमें पता था कि जी ओके इस पे एप्सिलॉन एक्स एक्स ये है, इस पे एप्सिलॉन वाई वाई ये है, और शेयर स्ट्रेन जो है गामा एक्स वाई की कोई वैल्यू आ रही है, तो इनको यूज करके ना हम कुछ एक सर्कल प्लॉट कर लेते होते थे। यू गाइस रिमेंबर दिस अ लिटिल बिट, थोड़ा थोड़ा आई होप याद आ रहा हो। एंड नाउ द पॉइंट वाज कि when we used to plot this let's say वो उसकी ओरिजिनल हमें ये 2 पॉइंट्स थे और इससे मिला था, इस सर्कल के ये एक्सट्रीम पॉइंट्स भी हैं which is showing me what my maximum value of the normal strain is. अगर किसी को याद नहीं है तो I'm happy to discuss this later on. It's not of direct relevance to us in this course, but I'm just trying to correlate कि if we just find our principal values using just टेंसर ऑपरेशंस, मतलब ये कि स्ट्रेन टेंसर की मैं आइगन वैल्यूज निकाल लूं तो वही चीज हमें मिल जाती है जो हम इतना लंबा चौड़ा वो स्ट्रेन ट्रांसफॉर्मेशन कर करके मैक्सिमम और मिनिमम निकाल रहे होते थे मोर सर्कल यूज करके एक जमाने में अपने आप लोगों के बचपन में बेसिकली। So these maxima and minima that we used to find using our Moore circle are actually exactly the same ones that are these principal strains which are being found using the sort of eigenvalue analysis for our strain tensor. And these represent the, as I said, the maximum and the minimum normal strains which are experienced at that for that particle. Okay. Okay, so बाकी थोड़ी सी और चीजें which I'm not going to focus on too much for strain. Instead वो जब हम stresses पे पहुंचेंगे then we'll focus on these a little bit more. So it's we'll discuss the principal strains will come up again. Don't worry if you guys don't remember Moore circle that much, but it will pop up again. Right. So this was just the remainder part which was left over from last time. मतलब at least from the topic of last time. I wasn't expecting कि हम पिछली दफा ये कर लेंगे. और for that I have a couple of examples that I would recommend that you guys do. तो lie की ये 2 examples and ready की 2 examples, not an assignment, you don't need to hand them in. This is just for you guys to know कि okay ये दोनों ये 4 examples जो हैं ये हमारे course से relevant हैं, the material that we've covered in the course. So after that we're gonna start looking at kinematic rates. So what I'm going to do is I'll take a break. It's been an hour now, so we'll take a break now at 6:20. So let's start up again at 6:30 basically. Okay, so 10-minute break for everybody. Right. Okay, everybody, welcome back. 6:30 p.m. So again, I thought कि maybe it's time. एक week गुजर गया था. Let's see कि SN को हम dethrone कर सकते हैं या नहीं. From what I recall, I think SN was the the winner, right? Just want to remind you guys that you do have to join this Kahoot game on another device. Please remember that, because याद रखें कि जो हमारी Microsoft Teams है, that is, oh, oh, oh no, where did my, oh yeah, oh, whew. जो हमारी Microsoft Teams है यहाँ पे, this is where we'll be seeing the questions pop up, right? And you guys have to respond on your own device. अलग से, तो आपको 2 डिवाइसें चाहिए. लैपटॉप के ऊपर आप क्वेश्चन देखें और मोबाइल के ऊपर उसको आंसर करें in the for the Kahoot. Okay, so there are 15 people here. Why there are loads of us? We need more competition. We know we need more competition. Okay, वरना it'll be too easy for us. And okay, so come on, people. I'm just gonna wait for a few more minutes, or just to get you guys prepared. The topic would be kinematics. So things that we've discussed over the last week and this week, essentially, yeah. Before we start off the next topic. For anyone who does not know how to access this, basically you just have to go to this website, kahoot.it, Kahoot it, and then enter this game pin, and you will be in. Or as before, I will just I'll go quiet, and then you guys can do your thing. Right, 18 people. Seems nobody else is. Muneeb, ऐसा कैसे possible है? Please try again. Oh, azan bhi again. Okay, we'll wait for the azan before starting.
أشهد أن لا إله إلا الله أشهد أن محمدا رسول الله أشهد أن محمدا رسول الله حي على الصلاة حي على الصلاة حي على الفلاح حي على الفلاح
Okay, जी चलें जी. मुनीब के अलावा तो loads of people have joined, so let's start and let's see how we get along. Okay, so everybody ready? अजान हो गई थी मेरी तरफ खत्म. I don't know आप लोगों को आवाज आ रही होती है मेरी साइड से या नहीं, लेकिन in any case, okay, so let's start. Oops. Alrighty, so looks like most of you answered, and majority did not get it correct, right? So kinematics is actually just these 7 people got it right. The yellow one, it's just the study of the geometric aspects of motion. Okay, only looking at कि okay उसकी पहले position ये थी, अब उसकी ये position होगी, उसकी velocity क्या है, acceleration क्या है, and that's about it basically. Or then from our aspects, looking at the deformations and the strains in there as well. But we are not looking at all what was causing that motion. As you might have noticed, so far we haven't talked at all about stresses or forces or anything of the like, right? So it's just the study of the geometric aspects of motion, nothing else. So that's what kinematics is. Okay. Right. Next question. Ready, set, go. Oh, sorry. Yes, just to remind you, the quicker you get your answers, the higher your score will be, in addition to it being required for it to be right. So it's a multi-select. Okay, maybe I did not give in enough time. Was this the issue of time, or did everybody just disappear to have more tea?
Ma'am,
Screen
the
was late to
screen
load.
wasn't loading.
And they got it correctly that when we're looking at stress, we're trying to find stress causing deformations. Then it has to be the right stretch tensor, U, the right Cauchy-Green deformation tensor, this C thing, and the green strain tensor. Because only in तीनों में rigid body displacement कोई effect नहीं. There's a deformation gradient था, that actually was being affected by rigid body deformations. So it was being affected by rigid body rotations, to be precise. Right, so that's why that was not correct, whereas these 3 are perfectly fine. But it's only that these 2 are actually much better and easily measured, whereas the right stretch tensor is very difficult to calculate. Okay, ये हुआ क्या था? Could somebody? No, okay.
मैम स्क्रीन बहुत लेट लोड हो रही है.
Okay, so next question. So Agile Penguin probably got that question because they were agile, you see, they were very quick. They got that right. Everybody else just didn't get it. Okay, next question. Good on most of you, very good. So anything being defined in the material description must be defined as a function of the original position, so the capital X, right? So these 3 people, please revise. The small x's are the current position. Okay, so material description is capital X. No, man, you're okay. For large deformation, the small strain tensor is used. Is this true or false? This was too easy, wasn't it? So large deformations. Oh, what? What I thought? Oh, I thought Apsab. Okay, sorry for assuming that. Right? No, please take a look even at just the sentence. So even if you knew nothing about tensors and strains and large and small displacement gradients, there's a large deformations. For large deformations, the small strain tensor is used. So that's not true, right? Uska naam hi, it's called the small strain tensor because it's only applicable when we have small deformation gradients. So jab hamare paas, when we've got large deformations, then what we tend to use is the green strain tensor. Okay? Right, there are just 6 questions in this quiz. So we're coming up to our second last question. I'll see who's at the top after this one. Oh, ye bichare ka thoda apologies for this. The small strain tensor is the dash part of the displacement gradient hona tha ye. I don't know what happened here. Of the displacement gradient. Excellent. Exactly right. As we just had recapped as well. और उसकी expression से भी हमें पता है. If we, oh, ये मेरी expression थोड़ी अजीब तरीके से आ रही है. This is the symmetric part of this ui comma j tensor. So it's the symmetric part of the displacement gradient. Well done. Right. So let's see second last question से पहले कि कौन सबसे top पे. Abdul Rahim, very good. And then your man, I'm guessing it's a man. So few women here. So is right behind you, and I think you can catch up as well. So let's see. Last question, say if there's any change in the standing. True or false? Okay, so we're split between the answers a bit, right? So the question is that if we already know we have a given displacement field, and if we use that displacement field to find our strains, then the strain field will be compatible. Now this is actually true. Why? Because as we discussed, the issue arises when we're going from the strain to the displacement. Whereas अगर हमारे पास हो ही unique displacement field already known हो, हमारा U1, U2, U3 known हो, फिर हमें कोई मसला नहीं है and we can straightforwardly find the strain. Or वो strain by definition, because it's being found or calculated by the unique displacement field, it will definitely be compatible. So this was actually true. अगर हमें हमारे पास displacement field known हो और उससे हम strain निकालें, वो strain हमेशा compatible होता है. Okay, if this is unclear to anyone, we can discuss this a bit further, but let's just see for now what the podium is. So third position, Essen, still at the podium spot though, that's good. And then Saad, well done to you. And then number 1 is, who's it gonna be? Abdur Rahim, well done, excellent. Abdur Rahim got 5 out of 6 correct. And then Saad and Essen got 4 out of 6. दूसरे 2 लोग और भी आए थे, which I missed who was there. It was HI and somebody else. And then where did Yo go? Yo का last question शायद गलत हो गया. But in any case, well done Abdur Rahim. फिर inshallah, let's see next time how you fare. Well done to you. Great work everybody. Okay, so let's let's get back to our slides where we were. पहले बल्कि let me just check if anybody has any questions regarding any other questions on the quiz. Okay, no questions maybe. All right. Okay, so let's get back to it. Right. Okay. So now we've sort of finished our spatial gradients part. मतलब ये कि thus far we had just been discussing finding gradients which were del, right? So del not हम find कर रहे थे, which were del with respect to del xi. Space में gradients निकाल रहे थे. So now what I want to move on to is actually finding. So that now what we're looking at is actually del by del t. And as we discussed last time, the reason, obviously, of course, we are interested in changes with respect to space and with respect to time, but also that these two things actually feature in two different fields a little bit. There's a heavier focus on them. So spatial gradients are more important in solid mechanics, whereas time gradients are more important in fluid mechanics. So, so that's what we're going to start off with. We're going to start to look at time derivatives of continuum, basically, of any continuum. So this is not just important in fluid mechanics, it actually also has importance in solid mechanics whenever we're looking at sort of the time dependent or dynamic behavior of materials. So then we need to take a look at the time rate of change, right? So let's start to do that. Now, of course, when we're doing that, then as मैंने अभी जैसे लिखा था, we're talking about differentiation with respect to time. Okay, so this is going to be मतलब एक किसी भी property की which is being described in space, उसका हम time derivative ले रहे होंगे. So let me explain what I mean by this. के एक field है which is described in space and then we're taking the time derivative of that. So the issue with something like that is, of course, let's consider अगर मैं I think maybe temperature is a good example. Let me just start off by temperature. So if I am describing the temperature of this body, or I am interested in the rate of change of temperature, let's say, then of course I am already presented with a choice, which is I could either represent that time in the material description or in the spatial description, right? या फिर in the Lagrangian description and the Eulerian description, and then be finding its time derivative. So this is actually a possibility for me. So of course, when I write it down, then I can write down that my same temperature field in the material description is something like so. Matlab it's a function of capital X1, X2, X3 and time. Whereas in my spatial description, then it's a function of the same time, sorry, the same sort of variable key field, the temperature field, could also be represented in terms of the small x's and time. Okay, now what I'm gonna do is to differentiate the two descriptions. I already have the capital X and small x, but I also want to emphasize this even further, and that's why I've got a hat for my material description and I've got a tilde for my spatial description. Now comes the interesting part, which is कि अगर मुझे इनका time derivative find करना हो, या rate of change find करना हो, then of course I can find the time derivative of either of these. So either I could find it in the material description or I could find it in the spatial description. And of course what that means is, क्योंकि याद रखें ना, derivative is the rate of changes with respect to time. मतलब ये कि partial derivation हो रही है with respect to time. What that means, of course, is कि whatever my function was, उसके बाकी सारे variables would be considered a constant, या फिर they would be considered to be fixed. Which is why I've written if I take the partial derivative of my temperature field in the material derivative, this one, material derivative का temperature field, then that is actually taking the partial derivative with respect to time, keeping capital X fixed or keeping capital X as a constant. Similarly, if I was to take the time derivative of my temperature field in the spatial description, then that actually means that I'm taking the time derivative of the tilde field, जो tilde से मैंने describe की थी, but this time around, small x would be fixed. So it's as if कि मैं इधर rate of change find कर रही हूँ. Oh no, actually not. Actually, I'll sorry. ये आखिरी line was a bit wrong, so I'll just leave it क्योंकि अभी हम discuss करेंगे कि physically what does that mean, right? But in any case, we do have to keep. If it's in the material derivative, we're going to be keeping the capital X fixed, whereas if it's in the spatial description, then we're going to be keeping the small x fixed to find these time derivatives. Right. Now, just as our description का नाम था material description and spatial description, उसी तरह हमारे in time derivatives का भी नाम है, which is के the one with the material description is known as the material time derivative. Not very imaginative, is it? It's very straightforward, right? So this where I'm keeping my capital X fixed is known as the material time derivative, or the important thing about it, as the name is implying, is that when I'm doing that, okay, when I'm fixing my capital X, then that's as if कि मैं इधर capital X fix कर लिया, एक particle को choose कर लिया, और उस particle का मैंने let's say पहले इसको मैं ना t hat याद रखिएगा, t hat है वो वाली, so मैं पहले उसका delta t hat by delta t find करूँगा, t is equals to 0, then I'm finding the rate of change of time of this particle. लेकिन फिर अगर मैं t is equals to 1 पे निकालूं, let's say, then t is equals to 1 पे, it's possible that this particle may have moved somewhere else, कहीं और चला गया वो space में, लेकिन I'm still finding इसी particle की, यही particle जो मैंने शुरू किया था, उसी का rate at t is equals to 1, which means that I was following this particle in time and I was finding its rate of change. And that's why this is somebody's mic is unmuted. Just let me complete one sentence literally and then you can ask. So that's why this is known as the material time derivative, because इसमें हम एक rate of change किसी property का find कर रहे हैं with respect to a particle. हम एक particle को follow कर रहे हैं और उसका rate of change find कर रहे हैं. Okay, and so there was a question, I think. Please. Oh, Hassan, sorry, I did not see this. Yes, very good. Strain tensor is just a gradient of displacement field. Is it okay? Umar, it is the gradient, लेकिन the gradient का function, मतलब ये it's not, मतलब sorry, what I mean to say that by that is कहीं just some corner which I can then cut out. But epsilon ij is not just, it's not equal to just this. Okay, it's actually इसका symmetric part, which is actually just half of ये ui comma j plus uj comma I. मतलब ये कि straight सीधा is not, it's not completely correct to say कि it's just the gradient of the displacement field. No, gradient of the displacement field तो ये del not u है. जो strain tensor है वो इस del not u का symmetric part है या फिर this thing right here. Okay.
Okay, ma'am.
Thank you. Okay, anybody else? Somebody had a question. अगर पूछना है तो please. जिन्होंने भी unmute किया था अपने आप को. अच्छा, अगर जब when you want to ask again, just message. Okay. No problem. Right. So we were just considering the rate of change in the material description हमने पहले consider किया था, and we saw कि how when we are writing this thing down, then this is actually the rate of change of a particle. ठीक है, हम एक particle को follow कर रहे होते हैं क्योंकि एक original x position को देख रहे हैं. Whereas now let's come to the other one. Let's come to us looking at the temperature field in the spatial description and then looking at its time derivative. Now, what does that mean? That means that my small x is fixed, which means that I'm just koi position in space thi, I've just fixed myself on here, let's say. Or what I'm doing is that I'm just looking at this, मैंने इसी x पे रहना है, small x के ऊपर. और अब I'm going to look at the rate of change of temperature with respect to time. Now, as you can imagine, this is known as the like चले spatial time derivative. लेकिन the other better version of that is the local rate of change. अभी इसका मतलब अभी clear हो जाएगा. Why is this the local rate of change? It is the local rate of change because I fixed my position in space and I'm just sitting here considering कि इसके through t is equals to 0 पे एक particle था, उसका क्या temperature change है, या फिर t is equals to 1 के ऊपर उसके उसी space पे मैंने उधर ही रहना है, कोई और particle आ गया, उसका क्या temperature का rate of change क्या है, फिर t is equals to through पे उसके through कोई और particle गुजर रहा होगा, उसका क्या rate of change है. That is basically I am just fixed on looking at the position in space and looking at how whoever or whatever is going through it at that point, what is the temperature basically, or what is the rate of change of temperature at that point. Does that make sense? So I fix my x position and I just look at that point in space, and when I'm talking about the rate of change of this temperature, then I'm just looking at the rate of change of temperature at this point in space. Okay? I hope कि ये दो चीजें आपको clear हो गई हैं. They're massively different in terms of the physical meaning. In one, I'm looking at the rate of change of a property of a particle, whereas in the other, I'm looking at the rate of change of that property at a fixed point in space. Right. Okay. So let's move on from these. हाँ जी.
मैम एक क्वेश्चन ये है कि हमने लास्ट टाइम जब स्टार्ट में पढ़े थे यही मटेरियल एंड स्पेशल डिस्क्रिप्शंस पढ़ी थी, तो उसमें यही चीज़ हमने उल्ट नहीं पढ़ी थी, तो इसमें अब ये चेंज हो गई है. नाउ द एक्स इज बीइंग फिक्स्ड. पहले हम ये कह रहे थे कि जब मटेरियल टाइम डेरिवेटिव मटेरियल का हम डिस्क्रिप्शन में आते थे तो हम यही कहते थे कि हम मतलब एक ही पॉइंट पर फिक्स्ड हैं और उस पॉइंट पर हम चेक कर रहे हैं. अब इसमें उल्ट हो गया है क्या? मुझे ये क्लियर नहीं हो रहा.
Adan, there must have been some misunderstanding because whenever we have talked about the material description capital X, then we are always saying कि अगर मैं किसी भी चीज को capital X से represent कर रही हूँ ना, then I'm saying कि I'm always referring back कि वो original कौन सा particle है, वो कहाँ पे बैठा हुआ था originally, और उसका temperature या anything that I'm describing. Please notice very carefully here कि no one is saying कि हम इस चीज का मतलब ये नहीं है. This is I think important to clarify. This is not saying that I'm just looking at the temperature at the original time or original position. What this is saying is कि एक पार्टिकल जिसकी ओरिजिनल पोजीशन xi थी उसका अब क्या टेम्परेचर है एट व्हाटएवर, अब उसकी जो भी नई पोजीशन हो, लेकिन उसकी ओरिजिनल पोजीशन ये थी. तो t इज इक्वल्स टू 0 पे वो यहाँ था, t इज इक्वल्स टू 1 पे उसने कहीं और होना है, लेकिन मैं उसको फिर भी आइडेंटिफाई कर रही हूंगी इसी से, such that here I would be finding t of xi at 0, whereas here I would be finding t of the same particle xi. ये जो xi है ना, ये नाम है उस particle, at t is equals to 1. ये बात क्लियर हो गई? सिर्फ मकसद ये है कि इस कैपिटल XI से आई एम ऑलवेज आइडेंटिफाइंग दैट पार्टिकल जो मैंने उसकी ओरिजिनल पोजीशन से उसको नाम दे दिया था. whereas when I am writing down my T tilde small xi comma t, then what I'm saying is कि अगर if I say this, let's say ये किसी चीज की ओरिजिनल पोजीशन थी और अब उसने कहीं जो भी टाइम पे चले जाना है, let's say new xi पे, then every time what I'm saying is कि I'm looking at a spatial position और उस पॉइंट का मैं कह रही हूँ कि क्या टेम्परेचर है. नॉट आई डोंट नो कि उसके थ्रू कौन सा पार्टिकल है इस वक्त या उधर उस वक्त कौन सा पार्टिकल लाई कर रहा है, राइट. विच मीन्स के आई कुड, इसीलिए वो जब लास्ट टाइम हमने डिस्कस किया था मैंने कोशिश की थी एक ओवरलैपिंग फिगर बनाने की, बिकॉज अगर मैं स्मॉल XI में लेट्स से इस पॉइंट को देख रही हूँ इस वाले, और एक ओरिजिनल बॉडी यूं थी और उसकी न्यू पोजीशन अब, मतलब ओरिजिनल में तो ये एक पॉइंट था ना इधर ही, और उसकी न्यू पोजीशन अब कंसिडर करें कि यहाँ से आगे चली गई है थोड़ी सी. अगर मैं स्मॉल XI को ही देखती रहूं, स्मॉल XI को, then clearly now there's a different part of the same body जो इस small XI पे है. ये बात क्लियर हुई? Which means that I am now looking at this point in space, not the original, the sort of the particle, not the fixed particle. X is fixed. What does that mean? Mahtab, that means when I'm taking the partial derivatives with respect to time, remember partial derivative का क्या मतलब होता है? That all other variables are kept constant, right? So if I'm taking it with respect to time, then I do need to fix the physical coordinates, yeah, physical description. और फिजिकली, मतलब फिजिकली से अब मेरा मतलब ये है कि उसको अगर हम रादर देन डेरिवेटिव्स की टर्म्स के अलावा, मतलब पार्शियल डेरिवेटिव्स की टर्म्स के अलावा, इफ आई एम टॉकिंग अबाउट इट जस्ट इन सॉर्ट ऑफ अंडरस्टैंडिंग व्हाट इट मींस फिजिकली, व्हाट इट मींस इज कि व्हेन आई एम कंसीडरिंग द material description capital X, then I'm keeping the capital X fixed, right? Which means that I have just fixed myself onto a particle, और उस particle का rate of change of temperature I'm looking at then. Whereas when I'm looking at the spatial या local rate of change, then in that case I fixed myself on a position in time. I fixed myself at a position in space, and then I'm looking at the rate of change of the field at that fixed point in space. I hope कि थोड़ा सा clear हो. एक और बात, कभी-कभी कोई चीजें, maybe if you talk to your colleagues as well, you guys are there to help each other out, okay? So पहले try to solve a problem yourself using textbooks. If it's not clear, then use your network of your colleagues to help solve it. And still, obviously, मुझसे भी आपने पूछना. I'm only saying कि कभी-कभी maybe someone else may say it in a way which may be more clear. So महताब, अगर अभी आपको clear ना हो ना, तो please do ask one of your friends or your colleagues. कि what does this mean to keep this fixed? Okay. Right. Let me move along. So I hope some bits are making sense. Hanji, a question? No? Okay. Right. Now the interesting part comes, which is कि जो material description का time derivative है ना, the material time derivative, that's actually a pretty important thing, and that's why उसका ना अपना एक नाम दिया जाता है. Whereas दूसरे वाले का ना थोड़ा सा आपने देखा था, मैं भी थोड़ी I was like, what should I call it? Local rate या spatial time derivative, या what should I call it? But this one is does not have a special name. Whereas the material time derivative is actually something which is pretty important. The reason being, of course, because it is the rate of change of a particular particle of the material itself, right? So as you can imagine, हमें तो उन particles से concern है ना, उस material से concern है. Which is why this time derivative, the material time derivative, is is pretty important and has its own name and has its own symbolic representation. So this material time derivative is represented using this dot. So जब हम ये dot use करते हैं ना, whenever we say, let's say, temperature field का material time derivative, then I just have t with a dot up there. Then that is referring to the material time derivative. Or to make it even more clear, sometimes we refer to it by the like so, using a capital D by capital DT. Now, please note that this is still a partial derivative with respect to time. Lekin because it was the partial derivative in the material description, that's why इसको खास differentiation देने के लिए, मतलब ये कि खास sort of identity देने के लिए, it is also represented like so with a capital D. है ये partial differentiation ही. Please do remember that. Okay, and if it is partial differentiation, then that means that I will be keeping my other variable, this capital X, fixed. So अब let's see कि हम ये material time derivative किस तरह find कर सकते हैं. Now let's first assume कि मेरे पास एक temperature field given ही material description में है. मतलब ये कि मुझे temperature पता ही वो particles का है, यू capital T करके. Then of course it's just straightforward. फिर तो मैं इसका d by dt find कर रही हूँ, such that जो भी उसकी expression होगी in terms of capital X, I can just differentiate it to find what my material derivative is. Okay, so this means कि अगर मेरा time was something like x1 plus x2 squared plus t x3, और इधर भी कोई t डाल देते हैं, just ऐसे t squared, then this description is in the material description, right? So which is why I can just find its t dot, सीधी सादी. It would just be 2t x1 plus x3, bas. This would be its time derivative, material time derivative, right? But if I had the temperature being described in the spatial description, that is tilde में defined होता, this small x के साथ, then अगर मुझे उसका time derivative निकालना, मुझे time derivative, मुझे उसका material time derivative निकालना है, तो फिर I need to do a little bit of manipulation. So what I need to then do is, this is too long और suddenly आ रहा है. Please, I'm sorry कि मैंने एक animation नहीं डाली. So just keep a pause and follow my cursor. ठीक है, एक करके, so that you guys can follow what's happening. So I'm saying that I'm still finding my material time derivative of temperature. Material time derivative का क्या मतलब होता है? It's the partial derivative with respect to time, but keeping capital X fixed. अब the only issue that I have is कि मेरी temperature field actually given है tilde के terms में, small x के terms में. So what I'm trying to do is कि I have a function of small x and I'm trying to differentiate it with respect to time, keeping this capital X fixed. So the only way to resolve this issue कि ये मैं small x को कैसे fix रख लूँ, मेरे पास तो capital X है जो मुझे fix रखना है, is to recall कि ये जो small x है, that can also be represented as a function of capital X, such that then I can use a chain rule. Or what that chain rule is, that if I want to find a function of small x का partial derivative with respect to time, keeping capital X fixed, then that is actually equal to Now look carefully, it's the chain rule being applied basically. It's actually, we take that same function and differentiate it keeping small x fixed पहले. That is, capital X वाला अभी बाद में आएगा. So पहले सिर्फ उसी itself का partial derivative. So partial derivative of t in terms of small x, keeping this small x fixed. So this is something we can calculate. Plus then we need to add on the chain rule terms. Plus what would it be? It would be the partial derivative of this temperature with respect to small xi multiplied by multiplied by the partial derivative of this small xi as a function of capital X, keeping capital X fixed. Okay, this is, I know it may look a bit complicated. Just please, I'm going to go quiet for a little, like a minute or so, and I just want you guys to look at this and see what's happening. ये देखें, इस चीज से के ऊपर जब chain rule apply करें, look at it. Just have a few minutes. Right, how is everybody doing? So let's see again. I hope ke aap logon, if you've taken some time, so things are making a little bit more sense. The issue was that I have my temperature field in terms of the small x, but my differentiation is happening with respect to capital X and time, where the partial is t, and hence capital X will be kept constant. Whereas my function is actually in terms of small x. तो फिर मुझे उसका किस तरह derivation find करनी होगी? And how we do that is this is basically the chain rule being applied, is that it's essentially उसी function का partial derivative with respect to the small x, plus then the derivative of the function with respect to the x, वो जो variable जिसको हम change कर रहे हैं, multiplied by the derivative of the variable that we're trying to replace, basically. Okay. I think if anybody is wondering why this is happening, I would really recommend that you go look at chain rule being applied for two variables, right? Two variables, and this is the issue. हमारे पास दो variables हैं, t और x, और उनमें से actually तीन variables हैं, लेकिन my point is कि the differentiation is with respect to two variables, and we need के जो हमारे पास एक वेरिएबल है ना, उसको कन्वर्ट करना है, so to speak, उसकी डिफरेंशिएशन को कन्वर्ट करना है into the capital X, and that's what we're trying to do right here. So you will, to be comfortable with this mathematically, if you are uncomfortable right now, please do look at chain rule for multiple variables. Okay. अभी तक कोई क्वेश्चन नहीं आया, इसलिए आए. Maybe this means that you all have understood it very well. Anybody, because I know that this is, at least for me, this is a little bit uncomfortable, so I have to look at it again and think about it very carefully. So would anybody जिसको लग रहा है कि उनको बिल्कुल clear grasp है, maybe you would like to explain this expansion in your own words, ताकि हमारे पास थोड़ी सी वैरायटी आ जाए, ताकि मे बी किसी को ना समझ आया तो आपके लफ्जों में समझ आ जाए. डू आई हैव एनी वॉलंटियर्स फॉर दैट? थैंक यू मुनीब. मुनीब ने चेन रूल डाल इधर पॉप कर दिया ताकि हमें नजर आ जाए. Okay. Chale, I'm hoping and guessing that you guys have understood it, so which is why I'll just carry on. So as always, my focus is कि हम उसकी maths को भी cater करें, but we also think about what these things are physically. So ab let me do that. So let's look at each of these terms and see what they mean physically. So first of all, what I'm not going to start from left to right. I'm actually going to jump from easy to hardest. Okay. So सबसे पहले मुझे ना आसान सी चीज को देखने दें. पहले इस term को देखते हैं और से. So this is the rate of change of xi of a particle, isn't it? This one. So small xi तो उसकी current position होती है एक किसी particle की, right? So the rate of change of the current position, isn't that of course just the velocity of a particle? So this term right here, when I'm looking at this del x by del t, keeping a particle fixed, or fixing, my point of view is from the particle, and that is basically me looking at the velocity of a particle in space. Perfect. So एक term तो हमें physically थोड़ी clear हो गई. Baki, or let's see now. Now I'm going to jump to this one. This one I've already discussed a little bit. So this is, I'm keeping my small x fixed. मतलब ये कि I fixed myself at a point in space. Could anyone please, if I'm fixed myself at a point in space and then I'm looking at the time derivative, what is this then? Isn't that the rate of change of the temperature at that fixed point in space? मतलब ये, it's just the rate at that point in space. ठीक? I fixed myself at a point and I'm looking at the rate of change of temperature. Now let's look at the last term. Now this one is, this is actually a sort of a geometric gradient. मतलब it's a gradient with respect to space. Right? It's del x, not del t. It's not a time derivative. और this spatial derivative, इसके बारे में थोड़ा सा आप लोगों को physically सोचना पड़ेगा. This is actually how the temperature field is changing in space. So that, now let's look at the global picture again. What were we trying to find? I was trying to find the rate of change of temperature, let's say, and this is the important part, rate of change of temperature of a particle. So what that rate of change of the temperature of a particle is turning out to be, अगर हमारे पास spatial description available हो, is actually, it's the summation of something, which is, it's the summation of the rate at a point in space, जहां पे वो particle currently है, plus how the temperature is changing in space multiplied by the velocity of the particle. Something very sort of complicated. Let me try to draw this out. Let's say कि मेरा ये कोई x y z मेरी कोई स्पेस है और मेरी ये कोई रेफरेंस कॉन्फ़िगरेशन थी ये वाली जिससे मैंने अपने पार्टिकल को चूज कर लिया है कि ये मेरा कैपिटल एक्स आई है किसी का, जो मैंने इसको फिक्स कर लिया और मुझे ना अब इस पार्टिकल का रेट ऑफ चेंज ऑफ टेम्परेचर फाइंड करना है जब टाइम इज 10 लेट्स से। अब लेट्स अज्यूम कि t इज इक्वल्स टू 10 के ऊपर ना ये साहब उठ के कहीं इधर पहुंच गए हैं। There's been some motion. Now I want to find this dt, capital dt by dt, लेकिन मेरा इशू ये है कि मुझे ना टेम्परेचर पता ही नहीं है विद रिस्पेक्ट टू द पार्टिकल्स। मुझे एक्चुअली टेम्परेचर स्पेस में पता है, पार्टिकल्स का नहीं पता, मुझे उसकी जस्ट स्पेशल डिस्क्रिप्शन पता है। एंड फिर इट मे बी कि कोई एक पार्टिकल उस पॉइंट से एक वक्त पे गुजर रहा, फिर कोई अगला पार्टिकल गुजर रहा, एंड सो ऑन, बट आई जस्ट नो इट एट पॉइंट्स इन स्पेस। So how I can use that description of temperature field to find the find the rate of change of temperature of a particular particle is by actually considering okay कि ये particle, ये मेरा xi है, ये अभी ना ये किसी space के अंदर कहाँ है, ये है actually एक किसी small xi के ऊपर। So what I'm going to do is in order to find its rate of change is कि पहले मैं ऐसा करूंगी कि ओके मैं इस पॉइंट के ऊपर स्पेस पे जो पॉइंट है उसका रेट ऑफ चेंज ऑफ टेम्परेचर फाइंड कर लेती हूँ पहले। ओ ये तो टाइम होना था, स्मॉल एक्स फिक्स्ड, मतलब ये कि उस स्पेशल पॉइंट पे टेम्परेचर का क्या रेट है वो फाइंड कर लिया। बट आई एक्चुअली वांट टू फाइंड नॉट I want to find the temperature of not this point in space but the particle that is that may be going through it at that particular time. So then उसको I gotta add on top of it कि वो जो particle इधर से गुजर रहा है उसकी क्या velocity है, कितनी तेजी से इधर से जा रहा है, and multiply it by at this point in space how was the temperature changing in xyz coordinates, मतलब space में कैसे the temperature was changing, not a spatial derivative but this. And when I find these, मतलब when I find this entire term, then I'm going to be able to find कि जो पार्टिकल कैपिटल एक्स आई उस पॉइंट इन स्पेस के थ्रू गुजर रहा था उसका क्या टाइम डेरिवेटिव है, उसका क्या रेट ऑफ चेंज ऑफ टेम्परेचर है। Okay, so this is a little bit more involved, or I'm trying to sort of elaborate on what these things physically are meaning ताकि हम लोगों को ये maths इसकी इतनी complicated ना लगे। The core issue that we're facing right now is that I want to find there's a particle that I'm interested in, and that particle maybe that's going through this point in space which is small xi, but I don't want कि मैं इस space के इस point के ऊपर अपना temperature derivative find कर रही हूँ क्योंकि उसके through कभी एक particle गुजरा, कभी दूसरा गुजरा, कभी तीसरा गुजरा, and so on. I want to find कि इस particle का कैसे temperature change हो रहा है with respect to time. So in order to do that, I actually need to find कि अच्छा वो particle space में जिस point से गुजर रहा है तो उसका क्या rate of change है, ठीक है, जिस point स्पेशल point के थ्रू वो गुजर रहा है उसका क्या rate of change of temperature है, प्लस कि वही टेम्परेचर स्पेस में चेंज कैसे हो रहा है मल्टीप्लाइड बाय कि वो पार्टिकल जो उसके थ्रू गुजर रहा है उसकी क्या वेलोसिटी है. ओके, राइट. सो दिस इज little complicated, I know. You guys have to think about this basically. But in any case, I'm going to erase what I've written just now. The deal is that if I want to find the material time derivative, that is, I want to find the time derivative keeping capital X fixed, when I don't know the temperature profile with respect to the particles, I know the temperature profile with respect to space, then I actually need to have this chain rule applied to it, okay? So it's just, there is physical meaning behind it. There is physical meaning behind the maths, but you just got to think very carefully about that, the physical sort of mechanism or understanding of it. Okay, so any questions? No? These things are pretty complicated. I don't understand how you guys don't have questions. मैं तो आपको बता रही हूँ and still I have questions and I'd like to know more. Okay, think about it, and inshallah next time as well we'll deal with this. Right, so this is just the result from my last slide. Just pointing out again ke that's the velocity. And what I'm going to do is I'm writing it in a little bit more compact form. So I already know that this is my velocity. So then what I've got is that my material derivative is just going to be the time derivative of this tilde field plus the velocity of the particle multiplied by the sort of the spatial gradient of temperature. In direct notation, this then becomes yes, the time derivative is as it is. याद रखें कि इंडेक्स नोटेशंस जो है वो स्पेस के कोऑर्डिनेट्स का कर रही होती है, राइट? डायरेक्शंस की डिपेंडेंस है, तो टाइम वाला तो जस्ट स्टेज एज इट इज, whereas for my जो जिनका ताल्लुक स्पेशल कोऑर्डिनेट्स या डायरेक्शन से है, they can be represented in indices or as direct notation like so. So this would have been vi del t with respect to xi. And if you notice, there's the I is the dummy index, and this is actually reducing the order of the tensor multiplication such that this is actually the dot product. So it's v dot del of t, which is pretty important, right? So this leads me next on to ke ab ye main velocity, I've brought this velocity up. So I think it's high time that we actually discuss velocity as well. Now, velocity, of course, we have to be a bit careful. Velocity kya hai? Velocity though is going to be a particle key, right? So it is by definition a material derivative. So it's never really going to, it's not going to be the velocity at a point in space, right? It's going to be the velocity of a particle that I'm looking at. So that is this capital D with dx with respect to dt. मतलब by definition है ही एक material derivative, the velocity of a particle.
Excuse me, ma'am.
Yes.
What about the velocities of a series of particles through a specific point in space?
Then that is not the then आपने खुद ही मुझे उसका जवाब दे दिया. Then we are looking at the velocity of multiple particles, aren't we?
Okay, thank you.
Right? Good question, very good. So यही मैं आपको कहना चाह रही हूँ कि जब हम velocity और acceleration की बात कर रहे हैं ना in kinematics, हम by definition कहते ही हैं कि velocity of a particle. I think हमने कभी notice नहीं किया होगा पहले, लेकिन हम बात ही एक पार्टिकल की वेलोसिटी और एक्सेलरेशन की कर रहे होते हैं. नेवर के एक पॉइंट इन स्पेस ये रहा और इस पे मैंने फिक्स कर लिया अपने आप को, और वेलोसिटी अभी जी इसके थ्रू ये पार्टिकल गुजरा, फिर ये गुजरा, फिर एंड सो ऑन. I am going to be interested in the particle, right? So even if I say कि अच्छा मैं space के इस point पे fix करके अपने आप को रख लूं, then all that's going to end up happening is that I'm still looking at this derivative, but I'm looking at different capital X's. मतलब ये कि I'm looking at different particles that may be going through that point. But at any one time, by my continuum definition, उसके थ्रू एक ही पार्टिकल जा रहा होगा. तो when I'm looking at t is equals to 10, t is equals to 10 पे इसके थ्रू I'm just going to have some one particle, right? So अगर मैं इसको कहने की कोशिश भी करूं कि मैं इस पॉइंट इन स्पेस पे देख रही हूँ, even then I will be looking at some fixed particle जिसकी velocity उस पॉइंट पे मैं नोट कर रही होंगी. So that's why I was referring to, okay, so it's just the rate of change of the current position of a particle. Hence why it's this capital D by small x. Now, please note, okay, just for the sake of it, if I do try, मैंने वो कहा था ना कि हम दोनों descriptions देख रहे होते हैं. So if I do try to find this thing, d capital X with respect to dt, this physically does not, what is this? Rate of change of the original position? X तो क्या original position थी ना? That's isn't that meaningless? Original position तो एक ही है जो starting point हमारी starting configuration थी. तो एक तो अव्वल तो ये कि ये तो zero हुआ ना, क्योंकि मतलब this capital X is the definition of the original. It's us giving the name to particles at the original position. So this thing makes no physical sense. It's only this, the current position of a particle जिसका हम rate of change find कर सकते हैं. So it's the small x के अंदर क्या change आ रहा है, which will give us the velocity of a particle. Perfect. So just wanted to point that out कि इसके अंदर इस case में this is the only thing that exists. Okay. So that is the velocity, but that moves us. Okay, so these are important results, of course. The big red boxes. Oh, that leads me to my example. Ooh, okay. Actually, I will. Thank you, Amir. You all understand. Let's do the example. I wanted to jump to the acceleration first. Take a second. Give me just a moment to see. Let's do the. Actually, if you allow me, I'm sorry for changing the order up. Can we define the acceleration first and then come to the example? Actually, I think by the time we end up defining the acceleration, we will run out of time. So इसलिए I want to get the sort of the theoretical part slightly out of the way, and then inshallah we will jump to the start off by you guys. आप लोगों ने क्योंकि सोचा होगा velocity और acceleration के बारे में, so we'll do the example then. So that's why let me jump to the acceleration. Okay. So if I want to find the acceleration, अब आते हैं थोड़ी सी tricky चीज के ऊपर, which is के acceleration भी again is going to be something defined for a particle. Okay. So I am interested in the acceleration of a particle, which of course is then the material derivative of the velocity. क्योंकि मैंने कहा ही ये है कि it's for a particle. So my capital X must be fixed. So then this is the material derivative. But the issue that can arise, as was the case for my temperature profile, इसके velocity जो है, that can actually be given in both either the material description या फिर the spatial description. Now what does that mean? पहले material को कर लेते हैं because that's easier to understand, which is why then I'll talk to you about the other one. So material description में मैं वही hat से represent कर देती हूँ. It means के I have my XYZ. I have my original body. और उससे I've defined the names of my particles. Now, if I'm looking at the velocity of, let's say, मैंने एक particular xi choose कर लिया है. मतलब ये कि ये xi था, इसको मैं कुछ और नाम दे देती हूँ. Let's say, let me call this one ai. ये ai particle है. तो अगर मैं ai की velocity निकालूं, तो I can find it at time 0. तब तो वो यही होगा ना. By the way, ये capital A इसीलिए लिखा है मैंने because it's representing its original position. फिर let's imagine कि I want to find the velocity of still this particle. मतलब ये still of AI. But now at time t is equals to 3 when it has moved somewhere here. Now I have no concern कि वो space में कहाँ चला गया है because मुझे उसकी velocity पता ही है in terms of its original position and time. Then in this sort of a definition, this is the material description of velocity. Okay, so for this I can differentiate it directly. Velocity was given in terms of x, or what's the word? I'm keeping capital X fixed. So I find my acceleration straightforward, no issue. But now let's consider the case जब मेरे पास actually velocity is known in the spatial description. Now what does that mean? Just as we had just been discussing a little while ago, that if I fix myself to a point in space, original uski, let's say ये configuration थी, but I have fixed myself to a small ai, जो कि ये जगह है space की. And then I look at the velocity at ai at time t is equals to 0. Then maybe उसके through कोई particle ना जा रहा और उसकी velocity कोई particle ही नहीं है, मतलब it's just it's 0. Then there's nothing going there. Maybe but maybe then I still keep myself fixed to this point in space and I find my velocity at t is equals to 3. Maybe अब उसके through ये वाला particle जा रहा था, ये खुशी खुशी इधर से गुजर रहा था. So then when I would have looked at this thing, I would have found the velocity of this particle as it was going through this point in space. ये original reference configuration थी, ये याद रखिएगा. But then if I keep myself fixed to this point and I still look at VAI, small ai, मतलब उसी fixed point in space, and I look at the velocity at 10, here there would have been a different particle going through it than before. अब उसके through maybe body का ये वाला particle जा रहा था. So that essentially I am repeatedly just looking at the velocity of different particles going through that fixed spatial point. And this sort of a description of velocity is my spatial description of velocity. और इस केस में हमें फिर से, अगर मुझे ये तो एक पॉइंट इन स्पेस के थ्रू जो भी पार्टिकल गुजर रहा था उसकी वेलोसिटी मिल रही थी, whereas अगर मुझे एक पार्टिकल की टू बिगिन विद वेलोसिटी फाइंड करनी होगी, then I get a little stuck and I have to go back to my chain rule जो मैंने टेम्परेचर के लिए भी किया था. Oh sorry, I apologize. If I have to find the acceleration of a particular particle, then I have to go back and use the chain rule, because if I'm trying to differentiate, if I'm trying to find the material derivative of this thing, मतलब ये velocity in terms of small x, but I'm trying to find it for a capital X, then then I have to use the chain rule. It doesn't, I cannot just directly differentiate this with respect to time keeping small x constant, because acceleration is not, that's not the acceleration of a particle basically then. So so then yes, so the point was that I can have my velocity field in the spatial description, and in that case then I have to use my chain rule as I did before, or जिस तरह पहले किया था उसी तरह we'll first get our time derivative keeping small x fixed, plus then we'll get the product of the gradient of the velocity field in space multiplied by the velocity of the particle which is passing through that point at that particular instance. Now ये चीजें क्या हो जाती हैं, ये this del x I by dex j ये velocity थी, so that's why I've just written it out as the velocity of a particle which is going through it. So this thing as before for the temperature field as well, हम इसी को भी मज़ीद index notation और direct notation में लिख सकते हैं. The only difference being कि when I was trying to find the time derivative, material time derivative of temperature, that was dt by dt, right? So that was a scalar field, whereas right now I'm trying to find dvi with respect to dt. So I'm trying to differentiate a vector field, which is why abhi in index notation I'm gonna have each of the acceleration components. ai होगा मेरे पास से, 3 components होंगे इसके, acceleration in the 1 direction, acceleration in the 2 direction, and acceleration in the 3 direction. And what that's equal to is the derivative of the velocity field described in just in space plus the velocity of a particle that's passing through that point multiplied by the derivative of the velocity with respect to space. And in direct notation, this is this expression right here. Please note the bold faces because these are tensors, they're vectors. So A ke 3 components and V ke 3 components and so on. Now, there's also another thing that's happening importantly, which is कि हमारे पास एक नया del operator define हो रहा है. कहते पहले हमारे पास del naught था, और I hope कि आप सब लोगों को अब याद है कि वो del naught इसलिए था because this was partial derivation with respect to capital X I. Whereas now I'm refining this del X, and this is the actual del operator, small x के लिहाज से, because this is del with respect to del small xi. Space में gradient, not with respect to original position, but space के अंदर जो gradient है. Right. Okay. So if this part about the acceleration being this is unclear, then it would really help कि आप जो हमने temperature field का material derivative देखा था उसको दोबारा revise करें to see what each of these terms mean or why we have to do this to find the material derivative. Yes. So again, just pointing this out again. Okay, this del x with respect to x जो है ना, this is a spatial मतलब Eulerian gradient है ये, Euler quantity है, because it's with respect to small x. Yes, and this is known as the velocity gradient. जिस तरह वो पहले हमने deformation gradient etc किए, वो सब material description के gradients थे, ये Lagrangian या spatial वाले हैं. Okay, right. So अब हमें acceleration भी आ गई है, और now then I'm gonna have some examples of each of velocity and acceleration to understand in depth what they are. Now the issue is got 10 minutes left. I'm actually inclined towards
next class में कर लेंगे मैम.
yeah, I'm also inclined towards that. There is a reason for this because you will just forget everything that we've discussed so far. So we will pick up these examples from next time. I repeat that please, you must all have gone through के velocity in the spatial or मटीरियल डिस्क्रिप्शन में उसका क्या मतलब है, एक्सेलरेशन को निकालने के लिए स्पेशल और मटीरियल अगर वेलोसिटी फील्ड हो तो फिर कैसे करेंगे, एंड सो ऑन. यू नीड टू गो थ्रू दिस टू अंडरस्टैंड के व्हाई डू वी हैव, व्हेनेवर वी आर ट्राइंग टू फाइंड द मटीरियल टाइम डेरिवेटिव, why are we getting these two different expressions for each of them. So why के अगर material gradient time derivative ही निकालना हो तो एक केस में बिल्कुल ये स्ट्रेट फॉरवर्ड सीधा साधा डिफरेंशिएशन है, and why in the other case we are applying the chain rule and it's coming out to be something a little bit complicated. And then also to think about again वही जो हमने temperature की example के लिए किया था, what these things actually mean physically. Okay, right. So we will inshallah we'll pick up here next time. Also, second comment, there is going to be an assignment for the kinematics part, but please note for this assignment the deadline will be 2 weeks time. 2 weeks, because उसके अंदर ना kinematics भी और kinematic rates भी हैं. So I will assign it either today or tomorrow, probably tomorrow. It's 8 p.m. right now. So I'll assign it tomorrow, and then just do take a look at it, okay? Not very long, just a few questions, 4 or 5 questions, that's about it. Right, okay, so that's the end for today. Loads of time derivatives we started to discuss. Inshallah, next time we'll pick up with some examples of these velocity and accelerations, and then start to see deformation gradients with respect to the rates of change of deformation gradients. ठीक है, वही जो f की जो deformation gradient की हमने बात की थी उसका rate of change कैसे निकालते हैं. So that's we'll pick up. All right, okay, so thank you everybody. I'm around for any questions.
I have a question, ma'am.
Ji, please.
Before acceleration, when we were doing a material derivative of velocity, we established that special derivative of the velocity is meaningless. But then we went on to have a derivative of special derivative of velocity in the acceleration part using the chain rule.
Excellent, excellent question. Let me explain what that means. So, completely right to ask this. Okay, so देखें, दो फर्क चीजें. एक है कि velocity जो है वो क्या चीज है? It's the rate of change of the position of a particle, right? So बात ये थी कि velocity itself को जब हमने derivation की terms में define करना हो तो फिर वो क्या होगा? Think about that. So if I am defining कि velocity किस चीज का derivative है? It is the derivative of the current position, right?
Yes, ma'am.
So it is this capital dx by dt. ऐसा ही है. और होगा क्या? होगा ये कि हमारे पास ये स्मॉल x गिवन कैसे होगा? हमारे पास होगा जी कि एक मेरा एक लेट्स से कोई ओरिजिनल पार्टिकल है जिसकी ओरिजिनल पोजीशन है x1, x2, x3. ठीक, अब उसकी करंट पोजीशन कुड बी गिवन लाइक समथिंग लाइक x1 जो है जी उसका है x1 प्लस 2t लेट्स से, और उसका करंट पोजीशन का x2 कोऑर्डिनेट जो है दैट्स x2 प्लस x3, कुछ भी ऐसे एंड सो ऑन, राइट? सो प्लीज नोटिस हियर कि वेलोसिटी का फिजिकली मतलब क्या होता है. वेलोसिटी मींस कि वो जो भी पार्टिकल था जिसकी मतलब ओरिजिनल पोजीशन तो ये रही, लेकिन उसकी करंट पोजीशन कैसे चेंज कर रही है विद रिस्पेक्ट टू टाइम. So that is why I'm saying that the velocity is actually this derivative of the small x with respect to time. for a fixed particle. ठीक? Now, what is possible, however, इसके ये इसके लिए आई मे बी हम एग्जाम्पल कर ही लेते तो थोड़ा सा बेहतर हो जाता, लेकिन चलें. नाउ कंसिडर, अभी मैं उसकी मैथमेटिकल उसकी बारे में बात नहीं करी. नाउ जस्ट कंसिडर वैसे कि अगर मेरे पास वेलोसिटी इज गिवन यूजिंग कैपिटल X एंड टाइम, एंड व्हाट दिस मींस, एज आई वाज सेइंग, कि हमारे पास एक पार्टिकल जिसकी ओरिजिनल कॉन्फ़िगरेशन ये है, और ये पार्टिकल मैंने चूज कर लिया, लेट्स से. So whenever I'm trying to find the velocity at time t is equals to 1, time t is equals to 2, t is equals to 3, then all that I'm doing is I'm saying कि मैंने इस particle को choose किया हुआ है, मैंने इसे fix किया हुआ है, और मैं कभी t is equals to 2 पे भी इसी का find कर रही हूँ, t is equals to 3 पे भी इसी की velocity find कर रही हूँ, बेशक वो space में पता नहीं कहाँ चला गया है. ठीक? So this would be the velocity in the capital X description. Whereas consider कि अगर मुझे यही मतलब एक velocity field small xi के terms में given होती, अब इस केस में what does this mean? This means अगर let's say कि मैं small xi fix कर लूँ, even though वो original body ये रही, but I've chosen a small xi which is, let's say, just for illustration purposes, somewhere here, and now I'm looking at के small xi पे time t is equals to 3 पे क्या velocity है. What that means is कि time t is equals to 3 पे उसके थ्रू जो पार्टिकल उस वक्त गुजर रहा था, मुझे उसकी वेलोसिटी मिल जाएगी. फिर लेट्स से मैं time t is equals to 5 का हूं, then what would happen is कि time t is equals to 5 पे उसके थ्रू कोई और पार्टिकल जा रहा था, मुझे उसकी वेलोसिटी पता चल जाएगी. लेकिन I've just sort of looking at the same point in space and looking at the different particles as they go through this point, and noting down their velocities. So my point being that this is just how they could be given to us as functions. When we are trying to find it, then it has to be the derivative of the small x with respect to keeping the capital X fixed. I'm sorry, Usama. I think na ye example, maybe I should have done it so it would have been more clear. Lekin okay, I promise you कि next time I'll pop in an example जिससे ये वाला जो part है ना aspect कि velocity itself in its definition it's the material derivative, but it is possible for us to have the velocity given either as in terms of the material description or in terms of the spatial descriptions. I will discuss this with an example ताकि it becomes more clear. Okay?
Thank you, ma'am.
No problem.